The microphone was turned off. Thank you, guys. Now, I'm going to repeat everything just in case. This is one of the most important results you're ever going to see, period. Probably the most important concept in this subject, the Fundamental Theorem of Calculus. We have a continuous function, it's integrable, and there's a function whose derivative is f. That's the second part is definitely the most important thing of it. So we're going to discuss some properties of definite integrals, and then we will put this bad boy into action. So to start with, we have this integral. Minus, this is the plus or minus. You know that we are integrating the same function, and we are picking up different intervals. We have A, we have B, and we have C. First of all, we are integrating here. Second of all, we are integrating here, in this direction, and here we are going backwards. Okay. So if we integrate in this interval and add these two integrals, we have integral from a to c of f of x plus integral from c to a of f of x. You can, if you change the sign here, the limits of the integral get swapped. Alternatively speaking, you can swap the limits of the integral by adding this. And so this castle of integrals is 0. Probably in a course called multiple variable calculus, you will see cases where a transformation like this allows you to integrate along circles or along different geometric figures, but this is not the case. We're working here with integrals. And so integral between A and B plus integral between B and C plus integral between C and A is a mathematics flavored donut. So I'm going to show number 2, which looks way more interesting. Minus of 3f of x dx. Okay, so what do we have here? Here we have the integral between 1 and 3 minus the integral between 1 and 2. So if we sum up these two, integral between 1 and 3 minus integral between 1 and 2, interval 1, 2, we subtract it from here. And this is the integral from 2 to 3 of 3f of x dx. You want to see it like this. We have 0, 1, 2, and 3. We integrate between 1 and 3. And then we subtract the integral between 1 and 2. So all that remains is the interval 2, 3. So our equation has become integral between 0 and 2 of 3f of x plus integral between 2 and 3 of 3f of x plus this thing over here. So we're going to add up those things, and we get integral between 0 and 3 of 3 f of x dx. We add this last term, which is integral between 0 and 3 of 2 f of x dx. And you know, one of the fundamental properties of the integration operator is that it's linear, which means the integral of 3 f of x minus the integral of 2 f of x in the same interval is this thing right here. I'm gonna write it down here. Now, questions. No questions. All right. So moving on, we have number 5. We are required to use elementary properties of the integral to calculate this thing right here. So x is continuous, so it's integrable, and there exists a function whose derivative is x. Which function has derivative x? Well, no other than x squared over 2. And that we evaluate from a to b. Now, if we want to interpret this as an area, we have that thing right here. Our integral is no other than this area here. Now, this distance here is b minus a. This distance here is a, and this distance here is b. Now, what's the formula for the surface of a rectangle trapeze? The formula for the surface of this is greater base plus smaller bases times height divided by 2. And what is this? This is sum times difference. Difference of squares. Now, questions about how we interpret the integrals as areas. I need a red pen. Do you guys see these green equations? Okay. Give me a second, please. Okay, this didn't work as expected. We will have to do with red, with green. So moving on. Now we are experiencing a serious problem in the form of I am absolutely unable to draw a function properly. So I'm going to skip exercises 7 and 9, but I find it very interesting that you check number 9 by yourselves. Now, for more fundamental properties of the integral, we know this. Which should come as no mystery whatsoever to all of you. And we can use that to calculate things like this. Integration is what? Linear. So the coefficients can come out of the operator. And so our integral is 2a cubed. Ooh, 19 is fun. Now, how is integration once again? Linear. So we can expand this integral Now, the best tip I can give you here is don't be afraid of variables. They're letters, and we most of the times we use them because it's the first one that comes to mind. X is the paradigmatic variable. T in physics means time, so we use it here and there. So don't be scared of variables. They just take values here and there. So the integral of this is for t evaluated between -2 and 2. And here we have to do a little transformation. Now this is 16. So I'm going to start writing it as 16 from now on. So moving here, we have 16, we have this thing right here. And now let's see what happens here. We have already this integral in this form, so we can use it. This is 16 plus minus a cubed over 3, in our case -2, and minus 2 cubed over 3. Now this is -8 over 3, -8 over 3, this is -16 over 3, plus 16. So this is 16 times 4/3, or equivalently 64 over 3. Now, questions about this type of place that we do with functions? All right. Okay. So in order to solve problem 21, we remember the fundamental property of integration. This already has this form. So it's worth 1/3. And now I want your ideas. How do we solve this equation? How do we integrate the square root of 1 minus x squared? Good. Good, but still. Okay. In order to solve this, there are many methods. I will try and show you all of them at some point. But first of all, what does this function represent? What is this? If we have -1 and 1 in this axis, and this is 1, this is the equation of a semicircle. And so what this integral represents is this part of the area. Okay, now what's the equation for the area of a quarter circle? The area of a quarter circle is pi r squared over 4. Why? The area of the full circle divided by 4, because it's only a fourth part. So this, I'm gonna write it down in English. It's 1/3. The area of a quarter circle with radius 1. What is that? Pi fourths. In general, if you remember it correctly, the square root of r squared minus x squared is a half circle with radius r. So in our case, we imagine that this one is a square, and we have our circle with radius 1. And so with this, we can already solve our integral. Our integral is 1/3 plus pi fourths. And you can leave it like that. So a very interesting application of this concept. It is good to know the tools, it's good to know the properties, but sometimes you have to remember what you are doing. You get lost in the trees that are the math, and you lose perspective of the forest that is the problem that you're solving. And so with this, now, these kind of tricks are very common in integration theory. So if you have questions about it, now is the time. Is there a way to solve it numerically? Yes, absolutely. You can either put these two numbers into a calculator, which gives you a numerical solution, or you can consider this as a Taylor polynomial, which has a big advantage, and is that integrate the sum of polynomials is just a sum of things like that. Will you get the exact answer? No, you never will, because there is an error inherent to Taylor polynomials, but it is faster, easier, and more importantly, more precise way to do it by looking at the functions as what they are, equations that describe curves. Also, if you use a computer, this may be practical, but you really don't want to start calculating this type of Taylor polynomials in the middle of an exam, for example, or for an article. You just apply fundamental properties and you get it in once. Could you try solving it by U substitution? Yes, you could. Actually, there is that's exactly the next step, the next episode. There is one change of variable here that will give you this, and yeah, we have time, so I actually can show you. So I'm going to call this method killing flies with a cannon. And with this, I mean, it's perfectly good to kill flies, but you definitely don't need a cannon for that. Now, the substitution we're doing here is sine of x equals u. If I remember correctly. X is the arcsine of u, so dx is 1 over square root 1 minus u squared du. When x equals 0, u equals 0. When x equals 1, u is pi halves. Right? No, u is not pi half, u is the arcsine of 1. It will make sense later. So by doing this change of variable, we move from 0. We go to this thing. Oh no, wait. Of course, it didn't make sense. The change of variable is x equals sine of u. So dx is cos u du. If x equals 0, u equals 0, if x equals 1, u is pi halves, which is what I want to do in the beginning. If you do the substitution, what you have here is the integral from 0 to pi over 2, 1 minus sine squared. That's cosine squared, okay? Witchcraft. Now, where do we go from here? In order to continue from here, there is one thing we have to remember. I only know 2 trigonometrical equations. I never get tired of saying so. This is one, and this is the other. And from here, if we sum these 2 equations, what we have is 2 cosine squared of u in one side and cosine 2u plus 1 in the other. So cosine squared of u is cosine of 2u plus 1 over 2. And this is something we can work with. Also me drawing brackets. That's something we can work with. So we substitute it here. Now, this thing can go out because integration is linear. And we have u over 2 evaluated between 0 and pi halves plus now, who tells me why this integral is equal to 0? Minus 1 plus 1. Okay, you got the idea. Now, this sum is pi over 4. And this integral, it's immediate, and it's 1/4 of that thing right here. Now, the sinus of 0 is 0. The sine of pi is also 0. So this equation is 1/4 of 0 plus 0. And so this full sum is nothing else than pi over 4. Again, that's not the tool I would use to kill a fly, but the fly's not there anymore. This would have been super useful to Walter White back in the day. So Is this possible to do by using U substitution? Yes. Yes. It's actually the paradigmatic example of U substitution. This type of, when you find this type of expressions, there is always a trigonometric substitution that kind of does the job for you. Do I recommend it? Not really. No, not really. However, here it is for you guys to enjoy. Funny enough, this represents the area of a quarter circle, as I said. If you change the integration limits, and here you put -1, you get the other half, and then by symmetry you multiply by 2, and that's how you get the popular area for the circle, pi r squared. If you put r squared here instead of 1, what you get is this thing right here. Lower left corner should be du and not u. You mean here? No, you mean here. And you are right. Never forget the differential. Like if you forget the differential, you are in deep trouble. Like you will look five seconds later to the same integral, and you won't know what in the world you're doing. So the differential here tells you what the variable is in an integral. So please never ever forget it. And okay, now I'm going to call this a 10-minute break, guys. So you have a little bit of time to stretch your actual muscles and not only your mathematical muscles, which are also important. And I'll see you back at 15 past. Okay, it's that time of the year. So there's this, an old man once said, I don't know how old he was or how long it has been since he said it, but he said, the way you prove movement is by walking. And now we're going to do exactly the same. So following this, we know that small integration rule, do we need more? Not for now. So let's see. We start with section 5.5, and I'm going to show you number 1 to begin with. Now, the derivative of this function is this function. Should be easy enough. This n+1 times n+1 and x with 1 degree less. So we arrive here. We're going to use that as our first integration rule. This is x4 over 4 evaluated between 0 and 2. And that's Nothing more and nothing else than a 4. Now for number 3. Now what problem do we have here? This square is in the denominator, so that may look like a complication, but we can see it as the integral between 1/2 and 1 of x in power minus 2 dx, different than minus 1, so we can apply our first integration rule, and that's minus 1 over x between 1/2 and 1. And that's minus 1 plus 2. Minus 1 minus, so plus 1 over 1/2 is 2. Number 6. Now, at this time, you're probably tired of hearing it, but how is integration? Linear. So it is actually the sum of two integrals. Now, exponent different than minus 1, exponent different than minus 1, we can apply our first integration rule. And this is minus 6x in power minus 2 minus 4, sorry. Derivative between 1 and 0 minus, and here we have is x cubed, it becomes x4 over 4. Evaluated between 1 and 2. Now, this is minus 4 over 4. And this is minus 4 over 1. So this part of the integral is 3. And here, evaluating 2, we have minus 2 in power 4, 16 divided by 8. 2 minus with this minus plus 1 over 8. So this thing in the end is 3 minus 2 plus 1 over 8. Now, questions about integrating sums of polynomials? Okay. Then let's move on. We're moving on to number 10. The integral from 0 to pi thirds of secant square theta differential of theta. Now, what do we do here? First of all, we figure out what this secant thing is. Much better. Now there's a possibility we may do cosine of theta equal t, and let's see what happens. Theta is arc cosine t. Differential of theta is this thing right here. If theta equals 0, t equals 1. If theta equals pi thirds, t is square root of 3 over 2. So let's do the substitution and see what it takes us. Okay. So first of all, we have that thing over there. We substitute it right. 1 over t squared with a minus, dt, and this thing right here. Now, this looks incredibly bad. Like in very, very bad. What I'm going to do is what is called a decomposition in simple fractions. And that will help us separate the two. So we have minus 1 over t squared, square root 1 minus t squared. This should be at plus b over t squared plus c over square root 1 minus t squared. Let's try with a decomposition like that and see what happens. So now at plus b, wait. Minus 1. And from here we have to do something that allows us to determine what the values of A, B, and C are. And from here we notice that there is no element in square root of 1 minus t squared. So I'm definitely doing something wrong here. Zero, 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 and that will be minus 1. So I'm not doing the proper approach. Let's try the other way around. A here and bt squared plus c here. Sometimes there's a lot of trial and error with these decompositions, and now that I see them, you can't see them. So let's try something like this and see what happens. We do the same thing. Cross product. Minus 1. So again, this is not working. Somebody tells me why? Nobody? Okay. So I'm going to do a trick here, and is this change of variable. And we assume that this is a over u plus b over square root of 1 minus u. Here we have an obvious problem. This is not a polynomial. So definitely a and b should not be coefficients, but maybe something completely different. We have a square root 1 minus u plus bu equal minus 1. That's correct. I'm having a small struggle with this one. Okay, so I'm going to give you an idea, and I will send you the coefficients via Canvas, so we can go on. The idea of this is that this is and once we have this this is minus a over t evaluated between 1 and square root of 3 divided by 2 plus this thing right here. And when at this point we can substitute and everything, and then we have to recover the change of variable. And I'm just not seeing the coefficients a and b here. Okay. Interesting. So this is the idea, but there is another idea. So if we put this in this form, then we could possibly have a quotient of functions, right? This looks like a function squared. This could be in the denominator, but what could be in the numerator? We look for a function f divided by g, and we know that its derivative, which is equal to f prime times g minus g prime times f divided by g squared. Is this. Okay, there might be many solutions to this equation, but first one, if g equals t, this equation becomes f prime times t minus f Is this a differential equation? It is a differential equation indeed. However, I'm going to do something a little bit different here because we are still not ready to solve this kind of differential equations. And I'm going to do this. You look at that? This is minus square root of 1 minus t squared minus t squared over that thing right here. Now, look at this. Do you remember when I told you last day and the day before that and the day before that and the day before that, and I'm not going to do any more repetitions because I cannot extend my arm anymore, that you have to know how to derivate perfectly in order to be able to integrate? Look at this. Look at the change that we're going to do here. Now, I'm going to admit it, this was a flex. I ate the minus sign somewhere in the way. Minus with that plus minus. Yeah, I have definitely messed up a minus sign anyway. So f is no other than minus square root of 1 over t squared. So our function f of t over g of t is no other than minus square root of 1 minus t squared divided by t. Now, this is the kind of argument that will save your life when everything goes wrong. Like, this is the equivalent of watching Mamma Mia where you are having a terrible day. It's always there. You won't use it all the time, but if you need it, it's always there. So this integral is none other than this function. Boom. Now we have to undo the transformation. So 1 minus cosine squared of theta evaluated between 0 and pi thirds. Now, tangent of x prime is the secant x squared, precisely. But think of it this way. Would you be able to solve it if you forgot it? If you forgot that the derivative of the tangent is 1 over cosine squared? And that's the point I want to make here. I actually forgot that the derivative of the tangent is secant squared, but we have weapons. Otherwise, I would have spent probably 30 or 45 minutes trying to figure out a solution. Would I eventually have succeeded? Who knows? But for now, let's call it an exercise. Hey, it was a fun one. Since the type of argument that you may or may not ever have to use, it's still good when it happens. Now, let's do one that is a little bit more relaxed to kind of unwind from this extremely creative endeavor. So the moral of this exciting story is derive it perfectly. Then you won't have this type of problems. Now, moving on, we have exercise 12. And that's the integral between 0 and 2 pi of 1 plus sine of u. Deep breath. Okay. This thing right here is 2 pi. This thing right here is minus cosine of u evaluated between 0 and 2 pi. Not bad in comparison, huh? Good advice, don't mess up. No, it's really not the morals of that story. The morals of that story is be prepared for everything, because it could happen. When I was preparing my university access exam, I had to fight an integral that was something similar to this. And it took me almost a week and a half to figure out how to solve that in 0 and pi, I think. And I was pretty damn ready for everything back then. So if you want to resume our fantastic and exciting adventure in one sentence, is be ready. Everybody, thanks for today. Thank you for coming, Nicholas. Have a nice day. Now let's do a couple more. Number 14. Now, This function is pretty easy to pretty easy to underderivate, because the derivative of the exponential is the exponential, and the derivative of the negative exponential is minus the negative exponential. So this is ex plus e minus x between minus 2 and 2. And what's that? E in power 2 plus e in power minus 2 minus e in power minus 2 and minus e in power 2. Simple, precise, beautiful, just the way I like it. Oh, funny. Now, I'm going to move on into number 33. And it's a question that could complicate things very much if you don't take the correct care of it. What happens if our function is defined piecewise? Like that. Now I'm going to draw here our goniometric circle and check the sign of the cosine. The sign of the cosine is positive in the first quadrant, negative in the second, negative in the third, and positive in the fourth. So what we have here is the absolute value of a positive amount between 0 and pi halves plus the absolute amount of a negative amount between pi halves and 3 pi halves. So this plus becomes a minus. Now, integral of the cosine, the sine. So let's see. Sine of pi halves, 1, minus sine of 0, still 1, minus sine of 3 pi halves, minus 1, minus with this minus plus, sine of pi half, which is 1. Sorry, this minus was here. So 1 minus 2, three. Now, questions about piecewise defined functions. No questions. All right. I hope the staff of the uni gave me a pile of perfect exams this morning. So I'm going to give you another exercise. I don't know if it's written in the book. There might be someone similar. But the exercise says find the area between f of x equals cosine x and the x axis for this. Now, you want to find the area below a curve. What you are going to do is integrate that curve. Who tells me the value of this integral without a calculator? Okay, I will tell you myself, it's 0. And you may be thinking, what's going on here? Then you will draw the curve. Your drawing will probably be better than mine, but you will notice that this area is different than 0. And now is when you look at the phrasing of the problem. Riemann integral only accounts for the area above the curve. What is happening here is that this area is considered positive, and this area, since it's below the axis, is considered negative. How do we fix that? We fix it in the following way. After we take our lessons in math, we notice the integral, function we notice that the function changes sign at x equal pi over 2. Wait. This is 2 pi. This is 2 pi. This is pi. And this is 2 pi. Important. So you take your lessons in math, you notice that that curve was not really defined to be the problem that I wanted it to be, but still we fixed the domain so it works. And we notice that the function changes sign. So in order for us to be able to consider this area using the integral, we have to flip it down. We have to flip it up. So our area is actually minus the function. We make negative become positive. How? With a minus sign. And from here we can start operating. And let's see what happens here. This is minus cosine of pi, which is 1, plus cosine of 0, which is 1, plus cosine of 2 pi, which is 1, minus cosine of pi, which is minus 1. And we're finished. So the area trapped between sine of x and the x-axis in the interval from 0 to 2 pi is 4. Now, last questions before we call this a day. Okay, I will rephrase it. Those of you who have questions but won't ask them now. How harsh will I be with assignment number 5? Well, I will have a certain amount of persons present assignment number 5. Let me see exactly how many. It was either really easy or extremely complicated. It has a little bit of both. It's the kind of assignment that allows me to differentiate who has studied the lessons and who hasn't. And with studied the lessons, I not only mean attended the lectures, but also taken a close look and done the exercise and tried. Exercise number 1, you have seen it today. Exercise number 2, we have done a very similar one in one of the tutorials. I don't know if it's tutorial number 5 or 6, but there's a very similar one there. And I'm not entirely sure, but I think you shouldn't have any sort of problem whatsoever with solving problem number 2. I cannot tell you anything else because that would be spoiling, and I'm against it. but I'm expecting you to have absolutely no trouble or an absolute mountain of trouble. So if you're having a mountain of trouble, my recommendation is that you throw the papers with the assignment you have done already away and start fresh. Because sometimes, you know, you start solving an exercise and you just don't see it, and you keep writing on the same paper, blah, 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 and then you flip the page and continue on that, and it only adds salt to the injury. So pick up all those drafts, throw them away, start fresh, and read the exercise carefully, because it's helping you way more than it looks like. Now, tomorrow in a workshop, I will be solving the exam. So for those of you who are interested in that, consider it. But if you're interested in having more details about how the exercises are solved and all that, just feel free to come by from 1 to 3. I'll do it from home. You already know how this works. So yeah, thank you very much for joining, guys. Now I'm going to trap myself with a pile of your exams and hope they are very good. See you tomorrow.